Thank you, everybody, for being here. So this is our physical oceanography community of practice meeting, of course. But we figured out that there is, of course, a lot of connections between the ocean, the atmosphere, and the ice. And so for this session in particular, we thought it would be very useful to have a couple of talks from two experts in atmospheric boundary layer and ice-ocean interaction, ice-ocean atmosphere interaction, sorry. And we have first, we go up is Florian Lemarié from the French Institute for Research in Computer Science and Applied Math. And Florian is going to talk to us about ice interaction in high-resolution ocean ice models. So it will be mostly a numerical talk, if I understand it right, and geared towards modeling. Next up, we have Christopher Cox from the Physical Science Laboratory of the U.S. National Oceanic and Atmospheric Administration. And that will be more of an observational point of view, if I understand it right. And Chris will be talking to us about some MOSAiC observations that have been performed and about the resiliency of the ice column to extreme warming events. Thank you again, everybody, for being here. And Florian, the floor is yours. If you want to share those slides, thank you very much.
Okay. Okay. Thank you for the introduction. Probably you see it full. Do you see it full screen? It's okay.
It's perfect. Thank you.
Okay. Thank you. So yes, this talk is about like an ongoing work actually toward an improvement for the representation of RC, and it was ready for RC at the beginning, but it could be also applied to the atmosphere over sea ice interactions in high resolution ocean ice global systems. So this work has been funded by the Copernicus program and also in part by the French Navy. So the general objective was to try to represent in an appropriate way the dynamical response of the surface wind stress to the sea surface and ice surface properties. So to have a good representation of that, actually, there are some important mechanisms that have been really identified. First, this is what we call the downward momentum mixing, which is a modulation of the atmospheric boundary layer turbulence by mesoscale sea surface temperature anomalies. So, for example, on the right here, I show that from a fully coupled simulation, like composite means for cyclonic ADs and anticyclonic ADs. And I see vertical profiles of the turbulent kinetic energy over those in the atmosphere over those ADs. And you can clearly see that when you have a cold anomaly, you tend to stabilize the atmospheric boundary layer. Actually, it's not really local to the surface. It goes all the way to 400 meters, for example. And we have when you have a warm anomaly, you tend to really destabilize the atmospheric boundary layer relatively strongly. Again, it has an effect up to here, 200 meters, for example. Another important process is atmospheric pressure adjustment, meaning that sea surface temperature is going to generate like a horizontal pressure gradient in the atmosphere, and this horizontal pressure gradient will affect the winds, the low-level winds. And another point is the coupling between the wind stress and sea surface currents, because actually when you compute wind stress, you account for the relative winds, so meaning the difference between the winds and the currents, and this dependence of wind stress to oceanic currents has a strong impact on the energetics at the RC interface. And now, if we want to represent those processes, first, if we look at the current practices to force an ocean model or ocean sea ice model, the widely spread approach is what I call here atmospheric surface layer forcing strategy, meaning that you impose like atmospheric data, usually at relatively large scale, at the top of the atmospheric surface layer, so probably around 10 meters. And then you have like what we call the bug formula or Monino book of simulated theory to compute the RC fluxes. But we can really easily show that in this case, the downward momentum mixing is underestimated because you don't have any freedom to represent here turbulence in the whole atmospheric boundary layer. The oceanic current feedback is overestimated. And if we think about the ice cover, actually there is in this case inconsistency between the ice cover simulated by your ocean sea ice model and the sea ice cover seen by your atmospheric data. So there is really a problem of consistency with this approach between the scales resolved by your model and the scale present in the surface fluxes. So of course, a straightforward way, let's say, to solve this issue is to use an interactive coupling with an atmospheric model. But to represent the fine structure in your in the fluxes, you need more or less the same resolution in the atmosphere and in the ocean ice model, which is almost unaffordable computationally for most applications. And there are issues with proper tuning atmospheric physics and also initialization issues. So our objective was to find an alternative approach that makes the atmospheric boundary layer more interactive while still maintaining some synoptic forcing from large-scale atmospheric data. So there has been some attempts, so I don't go into the details here to go in that direction, but those attempts actually does not provide any way to represent the process we want to represent here. This was really done for different purposes. So the idea is to go from what I described earlier, this atmospheric surface layer forcing strategy, where we impose atmospheric data, let's say at 10 meters, to go to what I call the ABL coupling strategy, where in this case, we just impose atmospheric data over the whole atmospheric boundary layer, but at the same time, we represent more or less the turbulence in the atmospheric boundary layer. So this will be a prognostic model that is what we can call guided by large-scale atmospheric data, either by operational weather forecast or reanalysis. Yes, that's the idea in this case. And so just maybe the basic idea is really to say, okay, we have access to large-scale atmospheric data computed with an atmospheric model using relatively low-resolution oceanic surface data. And we run a simulation where we have access to high-resolution oceanic data. So the idea is to combine those two information to be able to have like an estimate of what should be the high-resolution atmospheric value at 10 meters. So to build this surrogate model, you have different ways to do it. In our case, we really build a prognostic model, but you could also use, of course, machine learning strategy or try to do like sensitivity analysis to know what is the sensibility of your atmospheric model to modification in the oceanic data, for example. So we go for this prognostic model, and our really first attempt was really to focus on so to give up with to forget about this pressure adjustment mechanism and to focus on really the modulation of the turbulence in the atmosphere by sea surface temperature and sea surface current anomalies. So to do this, we did formulate a simplified model where we assume like a transparent atmosphere. So what it means is that here the focus is really on the turbulent components of the RC fluxes, and we keep the radiative forcing as it is used usually. We do like assumptions that are commonly accepted. I think the fact that vertical gradients are much larger than horizontal gradients in the atmospheric boundary layer, and the fact that the turbulent vertical transport is much more efficient than the vertical advection by the mean velocity. So we end up with a relatively simple model, so more or less a single column model in general. So it means that we couple each grid point of our ocean sea ice model with like a single column atmospheric boundary layer model, which is formulated like this. So the two important really ingredients are those red terms that corresponds to that are given by a turbulence closure. And also you have a forcing towards the large-scale data, which is formulated here as a spectral nudging. And the relaxation is very strong when you are above the boundary layer, atmospheric boundary layer, because in this case, this model is completely irrelevant and cannot represent anything properly. But it is less relaxed towards the surface to give more freedom to this ABL model. So there are more details in this GMD paper in 2021. I thought you would be interesting to do more a little bit about the turbulent closure scheme that has been chosen. So it has been adapted from one derived for the Météo France operational systems. So this is from Couxart et al. 2000. So this is a standard TKE prognostic TKE scheme with a diagnostic mixing length in this case. But we did record everything from scratch, more or less because our vertical coordinate is much simpler than the one from atmospheric models, and also to have better performance. And at the same time, we did impose some additional properties at the discrete level for this closure to guarantee, for example, the positivity of TKE, consistency with the Monino-Bukov surface layer theory to provide boundary condition for TKE in mincing length. And we have like an energy conserving discretization of the forcing term for the TKE equation. Just so this is a more technical part, sorry. So just to give you a few words about it, because I think it's important for the rest of the talk, is that the standard practice in the meteor-force models was to use
a CAC reader. Eric has a card deal.
Sorry? No? Okay. The Bugeaud and Nakarer length scale that is defined like this, so more or less. So the length scale is defined as a function of the upward mixing length and downward mixing length. And more or less how it is defined is for a given energy, we try to compute the distance that a parcel can travel actually with an initial TKE and for a given stratification. So we can derive a local version of it. This is a Deardorff length scale, which is just the square root of 2t multiplied by the TKE divided by the Born-Weishaler frequency. But the important aspect actually is that recently Rodier et al. Have introduced a modification of it to account for the vertical shear in the mixing length computation. And I will show later that it is a very important ingredient to properly represent very stable boundary layers, which is important for sure for high latitude regions. And what we did derive, because this kind of boundary of mixing length computed from those type of integrals, it's very costly in terms of computational cost. So we did derive the local version of it that takes this form. So this is more or less that an enhanced Deardorff length scale where we include the vertical stress, the vertical shear, sorry, on top of the effect of the stratification. So to validate this approach, to validate our closure, we did a lot of different test cases. So I will just talk about one particular one. This is the Goebbels 1 test case. This is a stably stratified boundary layer. And in this case, we have a large dissimulation available for this test. So this is described, for example, in this publication here. And basically just a single column experiment with a given initial profile for temperature here. You start from a temperature at the surface at minus 10 degrees Celsius, and then you have a decrease of temperature over time. And we look at the solution after 10 hours, and we compare it to the LES in a red here. So this is a single profile for temperature here, and velocity, the norm of the velocity of the winds here. So what I wanted to show is really the fact that if you use only a buoyancy-based length scale, you have really relatively large error compared to larger dissimulation, and it is much improved as soon as you include a dependency on the shear in the mixing length computation. So this is probably something that most of you already know. There is paper talking about it, but with our approach, really, we have just a very simple model, and we can easily really extend it and add new ingredients like this one to make it relevant, especially here for very strong, for very stable boundary layer. So this approach, because we are relatively happy with all the really single column test cases we did, has been implemented in the NEMO ocean model. So more or less the usual way in NEMO how things are coded is this one. You have the ocean component, you have a sea ice component, and then you compute fluxes through this atmospheric surface layer or bulk formulation using 10-meter atmospheric data. And what we do with our approach, in this case, the difference is that we use 3-dimensional atmospheric data for the first, let's say, 1,000 meters of the atmosphere, not for the whole atmospheric column, air column. And we did add this additional model on top of the bulk formulation. So it's relatively easy to implement. Actually, it's just 2 or 3 additional subroutines in NEMO. And it has been coded to have exactly the same computational grid between all the components here. And you can run also only what we call the surface module here as a standalone module. So you can just prescribe SST and sea surface current and still run this model to do like a testing or sensitivity and analysis. And the overhead is relatively more moderate in the fact that what is really, you have an additional 5% for CPU time and 10% for elapsed time, because actually the fact that you need to read 3-dimensional data is quite costly sometimes. It depends really on the architecture. And I don't detail here, but for the grid cell partially covered by sea ice, what we chose for the moment, it's the easiest way to go is to average the surface fluxes over each category. But actually, we are talking about now trying to have to run the whole atmospheric boundary layer over each categories, and then to average the AD viscosities and AD diffusibilities, actually. That will be the next step, actually. That is something we can relatively easily do with our approach. So for the validation, mostly here for the oceanic aspects, actually, for those simulations, we did ORCA 025, so quarter degree global simulations, so with NEMO. And we compare our result with some metrics from really fully coupled experiments. We look, for example, at the correlation between the 10-meter winds and SST to show that what we obtain with our system is relatively close to what we can get. So we try to find the same color panel as the one used here, color bar as the one used from those publications here. So this is really to validate the coupling between winds, 10-meter winds and SST. And the second aspect is the coupling with the surface currents. So we use here two coefficients from Renaud et al. So it's a little bit difficult to explain what it is exactly, but what you should know is that this SW parameter is exactly 0 if you use a bug formulation, or what I call the atmospheric surface layer forcing. And in this case, we can get something that is relatively consistent with model and data. And the same thing for this. So I don't go into the detail for those two metrics because it will take too much time, but we are relatively happy with what it gives for the coupling between sea surface current and the wind. And it's not really a validation, it's just so we looked also at how things behave at high latitudes, so for the Arctic and Antarctic region. So what I show here is the boundary layer height simulated by our ABL model and the ice cover that are the contours here. Just to show that we have really a smooth transition between ocean area and ice covered area. And what we see is that we really have the boundary layer is much thicker over the ocean than over sea ice. This is what we expect in this case. But we didn't really go into the details of the validation for this aspect because it was not the original purpose of our study. So now the ongoing work on this topic. So now it's possible with NEMO to run this type of simulation with this ABL1D models. There are all the pre-processing tools available, I think, to do that. So now the next step will be to try to relax this single column model assumption, because we know that for the near very strong SST fronts, for example, horizontal advection is very important in the atmospheric boundary layer. So the idea was to derive a three-dimensional model in this case. And I don't go into the details of the math here, but it has been done in a way that we formulate things in the form of a multiple scales asymptotics or multi-scale problem. So we have large scale this is a known state that are given, for example, by IRA5 or whatever IFS operational data. And you have microscales that are the scale of your high resolution oceanic or ocean sea ice model. And in this case, we just formulate it as a multi-scale problem, and we can know exactly what are the interactions between the different scales. And in the end, we end up with a equation set that is cast as we define it as a perturbation around really the large-scale data in practice. And during this derivation, what we were able to show is the fact that this ABL1D model is relevant to represent the fast temporal evolution at the micro timescales, but not, of course, the micro scales in space, because it's purely 1D, so it does not fill the horizontal scale. And we were able to have a 3D model that allows the representation of horizontal advection and also this pressure gradient adjustment mechanism. Just to show the improvement it can bring, actually. So I will go not through this one. So we did use like a relatively standardized test case by SPAL, first proposed by SPAL and adapted by Kilpatrick, of an atmospheric flow over a persistent mid-altitude SST front. So I show here the results. So this is altitude, and this is the X direction. So this is a 2D XZ test case. And this is for zonal winds and meridional winds at the end of the simulation. And in this case, I don't show it here, but the SST, there is an SST front. Where is it? So this one. Okay, there is an sorry, here. There is like an hyperbolic tangent. And it goes from cold side to the warm side of this SST front, actually. And what we see here is that we have this downward mixing process that is very important. So the boundary layer is relatively shallow on the cold side, and as soon as we go on the warm side, actually, it is much thicker, and you have an intensification of the wind. And here we have a reference, an LES simulation with the MOSAiC model, and we see that with this ABL 3D model, we are really able to represent it in a very good way, actually. And also, because what is important for us is really the 10-meter quantities, because this is what we use to compute the RC fluxes. And again, in the red here for zonal velocities, meridional velocities, and 10-meter temperature, with this three-dimensional ABL model, we really much improve. We have really much improved match with what the LES simulation are giving. And same thing, if we go now from the warm side to the cold side of the SST front, we have the same conclusion. Here, the dynamics is much more complicated because we go from unstable to stable. So there are some waves that are emitted and everything. But still, if we look at 10-meter quantities, we have a much better agreement with the LES simulation. So just to conclude and perspective, so we developed a simplified ABL model, and it has been really integrated to the NEMOS CICube model. So this is really a strategy that keeps the, let's say, computational efficiency and simplicity, let's say, and flexibility inherent to the ocean ice-only modeling. And it has been evaluated for standardized test cases and realistic Orca 025 simulations. And it was relatively relevant to represent what we call the thermal feedback effect and current feedback effect on the wind stress. So the good point is that the ABL 1D is relevant really to have a better representation of the fast temporal scales, but is not sensitive to the spatial scale. And we were able to derive a model that allows to account for now the main contribution to the momentum budget. But at that time, for the moment, it's not mature enough for realistic applications. And last slide, actually, specifically for ice-covered areas, we have adapted the TK scheme for very stable boundary layer following this Rodier paper. So we derive a local version of the boundary layer. With our approach, we have a more coherency between the ice cover simulated by the model and that seen by the simplified atmospheric boundary layer model. So it means we expect that the fluxes will be of better quality. And we are currently discussing with Pierre Rampal to really implement this approach in the framework of the SACIP project in general. So of course, at that time, what I don't know and what probably even Pierre doesn't really know is what should be the dominant process to represent in the momentum balance for the ABL over like partially ice-covered areas. Okay, this is what I wanted to say.
Thank you, Florian. Thank you very much. I suggest we go straight to Chris' talk, and then we will take questions toward the end, okay, if that's okay.
Okay.
Chris is all yours.
Okay, thank you. Good morning and afternoon, everyone. My name is Chris Cox. I'm a research scientist at NOAA's Physical Sciences Laboratory in Boulder, Colorado. I'm going to talk about actually, if you skip to the previous slide, a thermodynamic perspective complement the prior talk. Based on some observations during the MOSAiC expedition. I'll talk about that in a moment. This image here shows the passage of a warm front in mid-April 2020 at 84 degrees latitude north of Svalbard. This is part of a warm air advection event that was quite impactful on this expedition. And next slide. We did see also some dynamics associated with this event as well. And I had actually considered discussing air-ice stress interactions as part of this talk, although I won't have time for that today. Next slide. So MOSAiC was a drifting icebreaker expedition, multidisciplinary drifting observatory for the study of Arctic climate. This took place in 2019 and 2020. It was led by the Alfred Wegener Institute. It was a multinational, quite a large expedition, involved some hundreds of scientists. There were, this vessel was frozen into the sea ice north of the Laptev Sea in October 2019, and it was permitted to drift with the transpolar drift across the pole towards the North Atlantic during that year, and it exited into the East Greenland Sea at the end of July in 2020. The focus of this talk will be on that green part of the map, this leg that goes from the midwinter into the late spring. Next slide. So the team that I worked with, there were many measurements that were made by a large number of people during this expedition. The team I worked with was focused on measuring meteorology and air surface energetic interactions from the sea ice. This was led by the University of Colorado, my institution, NOAA as well, and we had some close collaborators in the Department of Energy, as well as some university collaborators, for example, with Dartmouth. And our objective was to measure meteorology, these air-ice interactions. We measured turbulent fluxes from this 10-meter tower, nearby radiation station. We also had a smaller single-level flux stations like the one shown in the background picture, which were mobile and autonomous. We were able to move those around and use them in different capacities. And I'm also in this presentation going to talk about some data that came from an SIMB3 that says sea ice, but it should be seasonal ice mass balance buoy. These buoys put out by the Dartmouth group collect measurements of the thermal temperature profiles through the ice. Next slide. So the interest here, the topic is melt onset. And what I mean by that is the onset of the summer melt season from the top side, so surface melt. This date marks the beginning of the summer melt season. It varies spatially. It also varies temporally. Variability temporally from year to year, something like 3 weeks. And it's because of that, it affects the duration of the melt season. So it also affects the amount of ice that's melted throughout the summer. Knowing this timing is also somewhat important for seasonally dependent activities, for seasonal planning, if you will. Frequently, it's thought to be affected by southerly advection. So it's that the initiation of this is thought to be associated with the advection of warm air from, in the example figure here, the North Pacific, but also on the Eastern Arctic from the North Atlantic. Warm, moist air, this moisture-laden air has this cloudy, low-level stratiform cloud cover, generally at a temperature about 0 Celsius, moving from the open ocean at lower latitudes out over the sea ice. This imparts a prolonged long wave and infrared pulse to the surface. And some studies have also speculated that these events, these advection events, when they don't actually trigger a melt onset, they can precondition the sea ice for an early melt season because they accelerate the warming of the subsurface, and some secondary effects as well. So that's the topic of this talk, is testing that hypothesis. Do these events actually act as a preconditioning effect on the sea ice? Next slide. So this time series, I realize there's no dates on the x-axis. At the left side is the beginning of March 2020, and the right side is the end of June. These show daily values of the net radiation. In the light bars, the dark bars are the net atmospheric forcing, so that's the net radiation minus the turbulence. In the wintertime, on the left side, it's a negative value, so this is the ice is cooling at the atmosphere. This is the growth period. On the right side, this is the summer period. Positive atmospheric forcing is during the melt season. And then there's some fuzzy transition in between. The red trace shows the surface skin temperature, and you can see I've marked by some purple arrows that at least after April, I've marked these events. For periods when we have atmospheric advection that's causing these warming pulses, you can see that there's a positive forcing associated with that for a few days as well. And then there's a couple important dates that occur on May 5th. One of these events causes the net radiation to turn positive for the summer. And then on May 13th, the net atmospheric forcing turns persistently positive for the summer. And then several weeks later, on May 25th, we get the melt onset. Next slide. And I think it'll be next slide again. Yeah. So that May 25th melt onset was canonical. It was associated with a low pressure system spinning up in the East Greenland Sea. The eastern flank of that system sent warm, moist air out over the sea ice, passing northward. The contour around the green dot being MOSAiC, that contour is the area that the satellite data suggests was affected by its melt onset as part of that event over the course of several days. Next slide. From MOSAiC, again, this sort of the red line we've seen before is zooming in on it. This is the surface temperature relative to the y-axis on the left. You can see when that melt onset occurs, if you just squint, you can see that there's a difference in the character of the surface temperature. So it's really quite clear to identify when this occurs. The blue line is the downwelling long wave and daily averages. Relative to the y-axis on the right, which I've scaled so that 315 watts per meter squared, which is about 0 Celsius, matches up with 273 Kelvin on the left. So you can see that warm cloud deck imparts this persistent long wave pulse on the surface, initiating that onset. And then the lower panel, it corresponds to a dearth of sunlight. So the short wave is decreased during that time. It's because it's optically thick cloud cover. So this is a long wave process. It initiates the onset. Next slide. That describes the onset, but the purpose here, we want to look at some of these early events and do they precondition the onset. So let's focus on the mid-April event, which is highlighted in this box. This is some 6 weeks prior to melt onset. The April event is this 2 back-to-back warming events that occur between about April 10 and 20. Next slide. It's actually generated quite a bit of interest from the MOSAiC community for various reasons. Early on, it was shown from Annette Rinke at Avi that if you look at the climatology of the area of MOSAiC in the ERA 5 reanalysis, there's daily records set in this area for warmth. So it's quite a strong and early season event. But what I'm showing here, and I don't have time to go into all the details, is a wavelet analysis. It's showing that what's truly anomalous about this isn't necessarily the synoptic variability of, in the 2 to 5 day time range. It's really the fact they're back-to-back events. So it's this prolonged period of warming, 10 to 12 days. It's really the anomalous part. So that prolonged period of warming imparts a prolonged pulse of warming into the surface. Next slide. So we already saw the top panel. The lower panel shows the data from that buoy. These are temperature profiles in the ice during this period. So during the winter period, it's cold at the surface. The ocean, of course, is stable, approximately 1.8 or so, 1.9 degrees Celsius. A lot of variability in the surface. And then when these warming events start occurring in the second half of the spring and the later spring, we see these pulses of warming coming from the top side of the profile, and over time that warming propagates downward into the ice. To measure what the impact is in the total uptake of energy for the ice, I integrated it in the bottom panel. So I chose March 11th as a date to start this integration. So it's like all relative to that date. That date was chosen because it's the date when the ice temperature, the mean core temperature of the ice reached its minimum for the winter. So it's all warming after that. So then we make some assumptions about density of snow and ice, and then we integrate the total energetic uptake in joules and aggregate that as a cumulative sum through the springtime as shown there in the lower panel. The yellow is the snow, the red is the ice, and the blue is a combination of the two. What this shows is that that April event was really impactful individually. It had some 40% of the total warming that the ice undergoes from its coldest point to melt onset over about 3 months. It happens in roughly a week to 10 days because of this event. But none of the other events that occur have anywhere near as impactful of a warming pulse. And so this event is actually quite a nice one to try to test to see if we can. It's a good candidate as a potential event for being a preconditioner of the melt onset. So next slide. So what we'll do is we're going to use just a very simple model here. This is a 1D diffusion model. It's just the heat equation. And we're going to force this model on the top with the observed skin temperature. We'll fix the ocean temperatures to, in this case, we set them to -2 Celsius. And then at some early point in the winter, we initialize this model using an observed temperature profile from that buoy. And then we allow it to evolve the temperatures within the ice and snow columns. So the top panel is the observations. The modeled temperatures are shown in the middle panel, and then the bottom shows the difference. It does a pretty good job. We have to make some assumptions about density and thermal conductivity, but we tune it a little bit, and we can get an RMSE of less than ½ a degree, which is perfectly good for the main purposes here, where we're looking for multiple tens of degrees Celsius shifts. You can see, though, that the difference is not, there's some systematic components to that difference, and if I have time, I might describe that a little bit later. Next slide. So we drive that model with the observed skin temperatures. That's the yellow line in the top panel, and then we want some counterfactual forcing to compare it to. So what we want out of that counterfactual forcing is an example of what the temperatures might have looked like had the mid-April event not occurred. So we get that temperature time series and splice it in, that's the purple, using a coupled forecast model that is an experimental model we use here at NOAA called the Coupled Arctic Forecast System. It's a WRF-based model. We initialize a forecast April 10th. We use an extended range forecast here we've artificially modified the forecast at the lateral boundaries of this model, which is regional, about 70 degrees north, by suppressing the northerly component of the winds. That prevents the advection from reaching the MOSAiC flow, and we get a temperature time series that we can use that is absent of this event. So we drive this 1D diffusion model with both of those temperature time series, and then we difference them on the bottom. And so the difference is shown there in that bottom panel. You can see so this shows us what the warming of the actual April event might have looked like relative to its absence. It propagates downward about 1.5 meters into the ice, and it lasts for some period of time. But importantly, it doesn't persist permanently. So next slide. So then we go through this exercise again, where we look at the thermal or the energetic uptake of the ice under these different scenarios. The blue line is what we already did. So that was the observations, and then the yellow line is this metric using the modeled core temperatures, and then the purple is the counterfactual. So you can see that these lines converge, and this is interesting because the observed forcing shows this rapid increase in temperature. Then it plateaus, so there isn't much uptake after that. Whereas for the counterfactual forcing, we see kind of this gradual increase over time. And each of these events that happens after the mid-April event, in particular the one right at the end of April on the 29th, and the one where the net radiation turns positive on May 5th, each contribute a bit more. And so these converge in time. How might we explain this? Next slide. The reason that this occurs is because by imposing that really strong warming during the mid-April event, the ice warms, right? But in doing so, it reduces the temperature gradient between the ocean and the surface, which suppresses the conduction from the ocean into the ice, and as well the conduction of atmospheric energy downward into the ice when warming events occur. So that suppressed conduction reduces the uptake of energy after the event would occur. So the rapid increase of energy that we get during such an event is countered by a reduced rate of uptake thereafter. So it comes at the expense of warming that you could have otherwise. So this constitutes a negative feedback. Warming events suppress the subsurface temperature gradient, reducing the heating rate thereafter. Next slide. So in the case of the mid-April event, it appears that it likely did not, could not have preconditioned the melt onset, because the memory of that event, if you will, was lost before we got even through the first week of May. So it goes pretty quick. And how quick might it go? Using, again, this diffusion model, so based on that perspective, we just bootstrapped a number of simulations of idealized events, an example of that shown on the left, and then attempted to calculate then an estimate of what the relaxation time back to the absence of the event would be. So that e-folding time is about a week, or in other words, the memory, if you will, of such an event is lost within the ice within about 10 days, about 80% of it's reduced. Next slide. So I'm not sure if I'm running out of time yet, but just very quickly, it's very speculative, that the difference that we saw in the model minus the IMB observations in the top there, which looked very systematic, was actually the shift in that bias from being negative to positive occurs during the mid-April event. So the mid-April event was accompanied by melt, just not a melt onset. It was a brief, about an hour's worth, but we did create wet snow, which then refreezes, and that changes the morphology of the snow. It changes its thermal conductivity, which was not something that we assumed that it was constant throughout for this experiment. If we modify the thermal conductivity using an estimate of what we think in the direction it should have gone, so we increase it, we can reduce the model minus observation differences. And so that may be one explanation for why we have these kind of systematic differences in the model minus buoy error. If that is the case, then next slide. There's some suggestion then that there's secondary effects. So if you have these events, they can produce an effect on the thermal conductivity, which then would itself also in a secondary way affect the uptake of energy, which appears to be in the same direction as the negative feedback, such that it's plausible that had this event not occurred, the warming rate actually might have been faster, such that you actually had a higher energetic content within the ice column by the 1st of May than had the event not occurred at all. Next slide. And advance again. I'm going to skip this one. So if it's not that these events are accelerating the warming of the ice, they're basically just changing the pathway that you get to 0 Celsius from the wintertime temperatures. What is it that might occur that might be a precursor to melt onset or be an essential factor? And I think that factor is the date that the net atmospheric forcing turns persistently positive, which for the MOSAiC flow is on May 13th. Next slide. The reason I think that is shown here, so these are profiles from that buoy. The white is the date, May 13th, and then reds are dates after that, some more summer-like profiles. Blues are dates before that, some more winter-like profiles. In the winter-like case, you have this flux that moves from the ocean through the ice towards the atmosphere, and it goes in that direction. After you get to persistent positive forcing from the atmosphere from above, you start turning that profile, it bows it. And so now you have a conduction coming downward persistently from above. So this convergence of fluxes rapidly warms the ice, and it moves its coldest point deeper into the ice, where it becomes more persistent. It would take longer for it to recover back to a winter state should the temperatures become colder above. That state is certainly a good precondition for persisting a melt. So I'd hypothesize that what likely prepares us for the melt onset in the ice column is that net atmospheric forcing turning persistently positive. And then once that happens, a persistent melt is ready. We're just waiting for a melt event to occur, after which feedbacks in the shortwave, for example, help persist it. Next slide. I think that's just my concluding slide. So yeah, just to conclude, the melt onsets observed at 25 May in 2020 for MOSAiC at 83 North. It's triggered by long wave processes. Prior to that, some 6 weeks of warming event, an advection event occurs that is responsible about 40% of the warming that we observed in the spring of 2020 for that ice flow. However, we believe there's a negative feedback in the temperature gradient that limits warming after these events. And thus, while the energy is retained within the ice from the event, this storage came at the cost of retaining energy later. And so we conclude that it likely did not precondition the MOSAiC flows for an earlier melt onset. There could be, sensitivity studies suggest there could be some snow morphology factors that are worth exploring further. And we hypothesize that instead of this preconditioning from these events, that we should be focusing on the net atmospheric forcing turning persistently positive and the variability in that date as a precursor for melt onset. Thank you.
Thank you, Chris. Thank you very much for this very interesting talk. If there is any question, please, you can either raise your hand or try to unmute yourself unless everybody comes at the same time. And we're happy to take questions. We have about, I think, 10 minutes, but we might go a little over in case.
I don't know where to raise my hand, so okay.
Go ahead.
Okay, I'm Jiao Wang, and then what is the counterfactual forcing from? Where is it from? Because it's a significant difference from the station in situ measurement.
Yes, that's intentional. So it came from the forecast model, but we artificially perturbed the winds at the lateral boundaries of the regional model to prevent the advection from occurring, so that we could produce a surface temperature time series that was a representation of that was counterfactual. So it's a representation of what might have occurred had this mid-April event not occurred. Honestly, the way that you select that counterfactual baseline doesn't impact the results very much.
Yeah.
The reason we chose to do the forecast model was so that we could account for coupled effects after the event, so that the surface temperature, even after the event is over, you still have a warm boundary layer.
So the forecast model is based on WRF, right?
Yeah.
I don't know. People know about WRF. I'm not WRF user, but I look at because I found several people use WRF to do the projection. They only can do 20 years at a time because the model, maybe because of the model is too diffusive. I don't know if people realize that or not. WRF is very dissipative, and So because I look at the menu, they use three big filters, and also the time integration scheme is along the Kuta scheme, and which is the fourth order in time, not so that will produce numerical or computational viscosity. So I don't know, the community over there is always no one raised this question, so I have to raise this question well, in different occasion. So do you have any comment on WRF? Because the community use WRF so popularly.
I don't have any comment. Sounds like you've thought about that quite a bit more than myself. I don't think that these factors are important for this experiment, though.
Oh no. And what I mean is just the WRF, because the forcing from WRF is so different from the the in situ measurement. So that is
yeah, but that's intentionally so. A forecast that's not artificially modified is much closer. I didn't show any validation of the model in this presentation.
Okay, thank you.
There's a question from Wilbur, if I see it right.
Yes, sure. Very nice presentations, Chris and Florian. Really enjoyed that. I have a question for Florian. Ocean sea ice models that are forced with atmospheric reanalysis or so, they usually suffer from like instability of in particular the overturning circulation. And in most models, that is kind of remedied by very artificial sea surface salinity restoring. I think that the main culprit is the lack of the feedback between ocean temperatures and the atmosphere. And I was wondering if your scheme would be actually resolving that issue, so that the ocean sea ice models might actually be able to run without that sea surface salinity restoring. I was hoping that you had some comments on that.
Actually, I think so, because it was not clear. Our objective was really to improve the wind stress, but at the same time, we also have we recompute also sensible heat flux and latent heat flux, actually. So it means that I think reply to a comment in the chat, the fact that really the stratification, the low over sea ice, it's really completely different from the ERA 5 stratification, for example. You really have the coupling at the bottom of the sea ice. So we could expect that in this case we have less, let's say, more consistency between the atmospheric and the fluxes and the really your sea ice cover, actually. For the instability you mentioned, I don't know. Actually, for the simulation we did with Orca 025, we didn't have any relaxation or whatever for the sea ice model, actually. It was really the standard SI cube model.
It's interesting. Thank you, Florian.
Yeah, you're welcome.
There's a question from Ailon.
Sorry. Yeah, I have a question for Chris. Chris, thank you very much for the very interesting work. I have a question about the change to snow conductivity, K, that parameter. Does that parameter also affect the surface fluxes calculation in the model, or just the snow ice model change?
No, in this case, so this isn't a coupled model. All this, the model that we were using is just a temperature diffusion model. So we prescribe the boundary condition. We also prescribe the thermal properties of the ice and the snow, which we just held them constant, which is the reason that you end up with this shift from a negative bias to a positive bias, because the actual thermal properties likely changed. I think now we're getting more results coming online from the experiment, and we might be able to better constrain that now with observations, whereas before it would have just been a guess, so we just held it constant.
Great. All right. Thank you.
Any other question? Well, I will take advantage of managing the meeting and ask one if I can. And that's a question for both, actually, for both Chris and Florian, probably. Chris, you mentioned how one of the main effects is the reduction of the gradient between the surface and the ocean, right? But then compensate for the lack of spike in your lack of increase in radiation, in heating, in energy uptake in your model. Do you think, would you think that Florian model, but represents much better the atmosphere of the ocean, would be useful to model this kind of phenomena in a isocean model, but doesn't resolve the entire atmosphere? I don't know if the question was.
Yeah, I mean, certainly anything is more sophisticated treatment than what I did, and I think that is an important next step. So yeah.
No, I didn't mean to. It's great what you did. I meant in case you usually run ocean models with a fixed atmospheric forcing, so we would not probably feel the kind of feedback that you've seen in your diffusion model, which is great.
Yeah. In addition, I mean, the reason that we use this, the purpose of this diffusion model, is because then we can specify many layers within the ice, so we can really resolve the movement of temperature of energy throughout the ice column. And so that's another simplification that a lot of models use, is they have very few layers, in some cases no snow at all, and so is a limited ability for a lot of sort of maybe operational coupled modeling to test this. But so if you can, I think you need to resolve not just the atmospheric processes, but also within the ice and snow columns, is what I'm saying.
Okay. So the ice column would be already a big improvement probably for a model. Okay. I think it's 8, so we are by the hour, unless there is a last very short question. I want to thank everybody for joining us for today, and in particular Chris and Florian for their talk. And we are looking forward to see you next month. And it will be about oceanic boundary layers, if I remember the program right. So we're moving atmospheric boundary layer, next time oceanic boundary layers. So thank you everybody for being here. Again, thank you to the speaker. Thank you, Tony, for helping organizing all this. And see you next month.
Thank you.
Thanks, everyone.
Everybody.
Thank you very much.